What would happen if, in space, the final frontier? Imagine a universe so vast, so extreme, that the rules of everyday life on Earth barely apply. Today, we will explore some of the most mind-blowing scenarios imaginable. Places where physics itself seems alien, environments that could obliterate life in an instant, and cosmic phenomena that challenge the imagination. Let's start with floating near a supermassive black hole. Black holes are regions where gravity is so intense that nothing can escape, not even light. If you approached one, your body would stretch and compress in an effect called spaghettification. Even hovering at the event horizon, radiation from the surrounding accretion disk would fry your body. Fun fact, the supermassive black hole at the center of the Milky Way, Sagittarius A, has a mass 4 million times that of the Sun. Light bends around it, stars appear distorted, and space-time is twisted beyond recognition. The visual alone would be breathtaking, deadly, but awe-inspiring. Next, consider standing on the surface of the Sun. The surface temperature is around 500 degrees Celsius, and the core reaches over 15 million degrees. Even a million miles away, radiation and heat are overwhelming. Any unprotected body would vaporize instantly. Solar flares can release as much energy as billions of nuclear bombs, and charged particles streaming from the Sun can fry electronics and living tissues at extreme distances. Imagine the blinding brilliance, the searing heat, and the incomprehensible scale. Even the most advanced spacecraft would be reduced to molten metal. Now, let's dive into the density of a neutron star. These are remnants of massive stars that have collapsed under their own gravity. A teaspoon of neutron star material weighs about 10 million tons. Gravity is approximately 2 billion times stronger than Earth's. Just stepping on the surface, or attempting to, would crush you instantly. Some neutron stars spin hundreds of times per second, producing magnetic fields trillions of times stronger than Earth's. Magnetars, as a type of neutron star, can emit gamma-ray bursts far more powerful than the Sun's lifetime output in seconds. Imagine the sheer forces at work, a place where matter itself is almost unrecognizable. What if you tried traveling at near light speed? According to Einstein's relativity, as you approach light speed, time slows relative to the outside universe. Stars stretch into lines, colors shift due to the Doppler effect, and time outside your spacecraft races ahead. A journey that takes hours for you could span decades or centuries outside. Imagine the universe morphing as you travel, stars bending, galaxies warping, and the cosmos revealing a surreal, almost artistic tapestry. Even at 99% of light speed, reaching Alpha Centauri would feel instantaneous for you, but decades would have passed outside. Picture spending a day in Jupiter's atmosphere. Its storms rage at 360 kilometers per hour, and the Great Red Spot has persisted for over 350 years. Gravity is 2.5 times that of Earth, making movement nearly impossible. Lightning storms erupt with ferocity thousands of times stronger than Earth's. The planet radiates more heat than it receives from the Sun, and the turbulent gas layers create crushing pressures. Landing or even floating within these clouds would be instant death. Imagine navigating through swirling gas, dodging lightning and feeling the relentless pull of immense gravity. Now, let's imagine floating unprotected in the vacuum of space. Within 15 seconds, you would lose consciousness. There is no air, no pressure, and temperatures swing from hundreds of degrees below freezing to extreme heat in sunlight. Cosmic rays bombard everything, traveling near light speed, capable of destroying molecular structures in your body. Survival without a protective suit is impossible. The void of space is absolute, silent, and deadly. A reminder of how fragile life truly is. Finally, consider witnessing a supernova, the explosive death of a star. In moments, a supernova releases more energy than the sun will produce in its entire lifetime. Shockwaves, radiation, and high-energy particles obliterate everything nearby. Even light years away, the energy is staggering. Supernovae also scatter heavy elements across the cosmos, gold, platinum, and more, forming the building blocks for planets and life. Observing one safely would be breathtaking. Light, outshining galaxies, matter and energy, creating chaos and beauty simultaneously. These extreme scenarios are only the beginning. The universe is full of places and events that defy comprehension. In the next part, we will venture into wormholes, quasars, rogue planets, and cosmic voids, exploring environments even stranger and more deadly than those we have seen so far. Floating through a stellar nursery, you would find yourself surrounded by dense clouds of gas and dust where new stars are born. Ultraviolet radiation from nearby young stars rips molecules apart instantly, and turbulent gas flows whip around you at thousands of kilometers per second. Temperatures vary wildly from near absolute zero in shadowed regions to tens of thousands of degrees in pockets heated by newborn stars. The beauty is mesmerizing. Neon pinks, deep blues, and golden glows shimmer across the nebula, sculpted by stellar winds. Yet, despite the visual spectacle, survival here without protection is impossible. The very matter that forms stars and planets would tear any human body apart in moments. Consider approaching a black hole merger. When two black holes collide, gravitational waves ripple outward, distorting space-time itself. The tidal forces near the merging black holes are extreme, stretching and compressing objects at the molecular level. Even light is bent and twisted, creating a surreal visual of warped stars and arcs of glowing matter. Any object too close would be torn apart by gravity before the collision even occurs. Observing from a safe distance, the event would emit energy equivalent to billions of suns, detectable billions of light years away. The sheer scale of such cosmic violence is almost incomprehensible. Floating near a dark matter concentration, you might notice nothing at first. The dark matter is invisible, but gravitationally, it pulls everything around it unpredictably. Your spacecraft or trajectory could shift suddenly as unseen masses tug at you, making navigation nearly impossible. Dark matter shapes galaxies, clusters, and the universe itself, yet its influence is subtle and invisible. One miscalculated step could leave you drifting endlessly, trapped in its invisible currents. A white dwarf appears deceptively small and calm. These stellar remnants pack a sun's mass into a sphere roughly the size of Earth. Surface gravity is extreme. A teaspoon of material weighs tons. Heat from the surface is intense, but at a safe distance, it glows with a pale, serene light. Approaching it too closely, however, you would feel the pull of gravity stretching matter. bending light and warping time ever so slightly. White dwarfs are laboratories of stellar evolution, showing how mass and density interact at the extreme edges of physics. A hypernova, the death of a supermassive star, unleashes gamma-ray bursts thousands of times stronger than ordinary supernovae. These bursts of energy can sterilize entire star systems, and the shockwave waves can tear apart surrounding clouds of gas and dust. Even from many light years away, the energy released is enough to damage electronic systems on planets. The hypernova's destruction is staggering, yet it is also a source of the universe's heaviest elements: platinum, gold, uranium, scattered across space to form planets and eventually life. Entering a quark-gluon plasma would expose matter to temperatures in the billions of degrees. Protons and neutrons dissolve into their fundamental constituents. Any material, including a spacecraft, would be obliterated instantly. While this state of matter is fleeting and primarily observed in particle accelerators, it represents the earliest moments of the universe, a glimpse into condition mere microseconds after the Big Bang. Imagine a cosmic ray storm originating from a nearby supernova remnant. High-energy particles moving at near light speed bombard everything in their path. They can destroy electronics, damage DNA, and cause chemical changes in molecules. The intensity of a storm like this can extend for light years, turning regions of space into hazardous zones for any life or technology. Cosmic rays are invisible and relentless, a reminder that even empty space is far from safe. A binary neutron star system spins rapidly around a shared center of gravity. The gravitational interactions produce strong tidal forces, and gamma-ray beams pulse outward with unerring precision. These systems can emit gravitational waves detectable across the universe. Approaching too closely, the radiation and tidal forces would be lethal. From a distance, however, the system serves as a cosmic clock, its pulses so regular that astronomers use them to measure time and navigate space. Drifting through a planetary nebula, the colorful remnants of a dying star, you would be surrounded by expanding clouds of ionized gas. The gases glow vividly. Reds, greens, and blues swirl in complex, changing patterns. But the expanding gas moves at high velocities, and radiation remains intense. Any unprotected observer would be shredded by the rapidly moving matter. Yet, these nebulae are some of the most visually stunning regions in the universe, revealing the beauty and chaos of stellar death simultaneously. Finally, interstellar comets and asteroids traverse space at incredible speeds, often tens of kilometers per second. Collisions at these velocities are catastrophic. Even small objects can obliterate planets. Navigating through such regions requires extreme precision. One collision could end any mission instantly. These tiny wanderers are reminders that space is not empty, but full of hidden hazards, moving at unimaginable velocities. Imagine venturing near a rogue planet, a world drifting through space without a star to orbit. Temperatures plunge near absolute zero, and any atmosphere freezes instantly. The surface, if solid, is a frozen wasteland, dark and silent. Life as we know it is impossible. Rogue planets wander the galaxy in complete isolation, reminding us of the utter emptiness and danger lurking in uncharted space. Even a spacecraft could face unpredictable gravitational tugs from unseen masses or faint nearby objects, making navigation a nightmare. Now, picture a journey through a cosmic void, the immense empty spaces between galaxy clusters. These voids are almost completely devoid of matter and light, with temperatures approaching absolute zero. Sound cannot travel. Radiation is minimal, yet cosmic rays occasionally penetrate, moving unchecked through millions of light years. The scale is incomprehensible. Distances so vast that light would take millions of years to cross them. Floating here, you would be utterly alone, a tiny speck in a yawning emptiness. Psychological isolation would be as extreme as any physical danger. Consider approaching a magnetar, an extremely magnetic neutron star. Its magnetic field is trillions of times stronger than Earth's. These forces can distort atoms and generate intense X-ray and gamma-ray bursts. Even light years away, the magnetars' radiation could disrupt electronics or damage biological tissue. Magnetars flare unpredictably, releasing energy equivalent to the sun's total output over 100,000 years in mere seconds. Visualizing one, you would see a tiny dense star with unimaginable power radiating deadly energy across the cosmos. A pulsar, another type of neutron star, spins hundreds of times per second, emitting beams of radiation with clock-like precision. If the beam struck you, it could fry unshielded matter instantly. Pulsars act as cosmic timekeepers. Their steady pulses allow astronomers to measure distances and track gravitational waves. Being near one would be terrifying, yet educational, a lesson in the precision and power inherent in extreme astrophysical objects. Imagine witnessing a stellar collision, where two neutron stars crash together. The impact produces gravitational waves and gamma-ray bursts so intense they could sterilize planets thousands of light years away. Kilonovae light up the universe, scattering elements like gold and platinum into space. Observing safely, the spectacle is breathtaking, a violent, brilliant event that seeds the cosmos with the building blocks of planets and life. Now let's enter the vicinity of a quasar, the active center of a distant galaxy powered by a supermassive black hole. Quasars emit more energy than entire galaxies. High-energy jets move near the speed of light, capable of annihilating anything in their path. Radiation levels near a quasar are lethal, and the gravitational forces warp space-time. Even billions of light years away, the brightness allows observation from Earth. Up close, the jets and radiant power are unimaginable, a reminder of how energetic and dangerous the universe can be. Consider navigating near a hypervelocity star, a star moving faster than 1,000 kilometers per second. These stars can escape their galaxy entirely, traveling through intergalactic space. Colliding with such an object would obliterate anything in its path. The forces at play, combined with extreme velocities, make encounters with these stars extremely hazardous. Watching one fly by, you witness both the dynamic motion of stars and the violence of cosmic mechanics. Imagine a journey to a supermassive black hole in a distant galaxy. These black holes contain billions of times the sun's mass. Gravity near the accretion disk is overwhelming, while radiation from the surrounding hot gas can destroy any spacecraft. Gravitational lensing bends light from nearby stars, creating surreal, distorted visuals. Observing safely from afar, you would see a warped panorama of cosmic light and matter circling a dark, bottomless center. The scale and power are beyond human comprehension. Finally, picture a region of exotic matter, hypothesized to exist in the universe. Exotic matter might allow phenomena like stable wormholes, but it would also exhibit gravitational properties contrary to ordinary matter. Interacting with such regions would be unpredictable. Objects might levitate, collapse, or be torn apart by unknown forces. Though speculative, it demonstrates that the universe may harbor places where physics as we know it is only partially valid, and reality behaves in ways humans cannot yet fully predict. Imagine drifting near a collapsing star, a massive star at the brink of turning into a black hole. Its core contracts rapidly. Temperatures soar into the millions of degrees, and intense radiation is emitted. Any unprotected observer would be incinerated instantly. Surrounding gases are blasted outward, forming shock waves that travel at thousands of kilometers per second, tearing apart nearby matter. Observing safely from a distance, you would witness a cosmic transformation, a brilliant, violent display that reshapes the neighborhood of stars and gas clouds. Consider a white hole, a hypothetical opposite of a black hole. While purely theoretical, a white hole would expel matter and energy instead of absorbing it. Approaching one, you could be bombarded by streams of high-energy particles moving at near-light speed. The extreme forces would tear apart any spacecraft, and radiation would be instantly lethal. White holes illustrate the extremes of theoretical physics and the possibilities that remain unexplored in our universe. Picture a supernova remnant from a massive star that exploded thousands of years ago. Shockwaves have cleared surrounding space of dust and gas, leaving behind expanding clouds of glowing plasma. High-energy particles continue to race through space, and radiation remains intense. Floating here, you would be surrounded by both the remnants of destruction and the beauty of cosmic art. Filaments of glowing gas, in reds, blues and purples, sculpted by magnetic fields and past explosions. Imagine approaching a tidal disruption event where a star gets too close to a supermassive black hole and is torn apart. Stellar matter stretches into a thin stream, spiraling into the black hole. Enormous amounts of energy are released, producing bright flares detectable across billions of light years. Any object too close would be shredded by tidal forces and radiation. Observing from a safe distance, you would see a spectacular, violent ballet of light and gravity, showing the destructive power of massive objects. Consider exploring a dense asteroid field at interstellar speed. Millions of rocks, ranging from pebble-sized to mountain-sized, move at tens of kilometers per second. Collisions are catastrophic. Navigation requires extreme precision and constant adjustments, as even a tiny rock could destroy a spacecraft instantly. The field is a chaotic, shifting labyrinth, visually striking but deadly. Picture traveling near a gamma-ray burst, GRB. These bursts are brief, extremely energetic emissions of gamma radiation, typically originating from collapsing massive stars or merging neutron stars. A GRB pointed directly at a planet could sterilize it in seconds. The radiation is so intense that even distant bursts are detectable billions of light years away. Flying through or near one without protection would be fatal. Observing safely from afar, the burst is a powerful flash, illuminating the cosmos in an instant. Imagine encountering a fast radio burst, FRB, a sudden, mysterious emission of radio waves from distant galaxies. These bursts last only milliseconds, but carry enormous energy. Their origins remain largely unknown, possibly involving magnetars or exotic cosmic events. Approaching the source too closely could expose you to deadly radiation or intense gravitational forces. FRBs highlight that the universe still holds secrets beyond our understanding. Consider entering a binary black hole system where two black holes orbit each other. Gravitational interactions create intense space-time distortions, bending light in strange, beautiful arcs. Matter spiraling between them is shredded by tidal forces, emitting powerful X-rays and gamma rays. Navigating near such a system without theoretical technology would be impossible. The visual effect, however, would be mesmerizing. Swirling streams of matter and light dancing around the dark cores. Finally, imagine a region of antimatter clouds where matter and antimatter coexist in precarious balance. Any contact between matter and antimatter releases energy equivalent to thousands of nuclear bombs. A single misstep in such a region would result in total annihilation. While largely theoretical in large clouds, antimatter offers insight into cosmic symmetry and the fundamental nature of the universe. Next, consider a fast-moving, intergalactic gas stream, moving at thousands of kilometers per second. Such streams can strip atmospheres from planets, disrupt stellar systems, and inject high-energy particles into nearby regions. Floating within one would be deadly. Yet from a distance, these streams sculpt galaxies and influence star formation, showing how motion at cosmic scales shapes the universe. Imagine a journey into a region of extreme gravitational lensing, where massive galaxy clusters bend light from objects behind them. Stars, galaxies, and nebulae appear stretched, duplicated, or twisted into arcs and rings. Floating here, your perception of space and distance would be distorted beyond recognition. Time itself is affected subtly, and light moves along curved paths, creating surreal cosmic vistas. Now, picture encountering a rogue black hole, wandering through interstellar space without orbiting a galaxy. Its gravity is intense, pulling nearby stars, planets, and gas along its path. Approaching too closely would result in spaghettification, but from afar, the black hole warps light, creating eerie, curved views of the stars behind it. Rogue black holes remind us that even in empty space, invisible dangers lurk. Consider drifting through a dense molecular cloud, the birthplace of stars and planetary systems. Temperatures are low, but radiation from nearby newborn stars creates pockets of extreme energy. Dust and gas particles collide at high speeds, generating shock waves and radiation. Unprotected, you would be torn apart, yet the cloud is visually stunning. Billowing arcs of color and light that hint at future solar systems and planets. Imagine floating near a magnetic flux tube from a magnetar, a channel of concentrated magnetic energy. Atoms are distorted, radiation levels spike, and the environment becomes instantly lethal. Even at a distance, the visual spectacle is extraordinary. Glowing streams of charged particles dance along invisible lines of magnetic force, sculpting the surrounding space into luminous, surreal forms. Now, let's explore a supermassive black hole with an accretion disk feeding it, where matter spirals inward at near-light speed. Friction heats the material to millions of degrees, producing X-rays and gamma rays. The gravitational pull bends light, creating warped, twisted views of surrounding stars. Any object venturing too close would be torn apart, yet from a safe distance, the swirling disk is one of the most beautiful and violent structures in the universe. Finally, picture returning to more familiar territory. Observing Earth from orbit. After journeys through black holes, neutron stars, supernovae, quasars, and cosmic voids. Compared to the extremes of the universe, our planet is fragile yet beautiful. Life thrives here, delicately balanced amidst forces that elsewhere could obliterate existence instantly. The universe is vast, dangerous, and full of mysteries, yet Earth is a sanctuary, a home for exploration and curiosity. These scenarios reveal the full spectrum of cosmic extremes, from violent deaths of stars to theoretical cosmic strings, from drifting rogue planets to gamma-ray bursts. Space is simultaneously beautiful, terrifying, and awe-inspiring. Every extreme event reminds us of our fragility, the power of natural forces, and the endless opportunities to learn, explore, and marvel at the universe. Which of these cosmic phenomena fascinates or terrifies you the most?